speak to us on automorphic Levi-Sobolev spaces.
Italian guy.
And self-adjoint operators.
Thank you, Peter, and thanks for the kind invitation. And so what I'll be talking about, should do this and then up, right, or vice versa. Anyway, so some of this, or really this is what I'll talk about, are some stories that are background with Enrico Bombieri. And I thank him for his kindness and generosity, but also in particular then, given that if I'm trying to tell stories of the background that motivated the considerations, then of course interpretations are much more subjective. You know, it's a matter of taste. So you should not attribute to Professor Bombieri anything that I say that seems a little marginal. But so what I wanted to do is first tell some phenomena, and anticipating that maybe there are some people here who aren't number theorists or people who aren't practiced analysts, then I'll try to tell these stories in as straightforward a way as possible, but still illustrating the thing that caught people's attention. And then after that, to explain things better, because a lot of these phenomena were provocative but confusing. So then to explain better, there's some sort of analytic grounding that one can do, which is mostly, I would claim, pretty standard mathematics, except maybe not so often juxtaposed with issues that come up in number theory, or maybe only kind of shyly juxtaposed. And if you're a little more aggressive, perhaps it's more effective. And then hopefully we can at least explain, as one virtue of that viewpoint, we can explicate these otherwise sort of confusing but provocative examples. So explicate the phenomena. And then if the explication seems really convincing, then you imagine maybe we can do some more things. So I hope I'll have time to say a little about this, but really the stories from 30 years ago are quite suggestive already, and for a sort of mixed audience, or if you haven't seen these things, it's quite interesting, I think. So there are several types of phenomena that everybody's acquainted, well, some everybody's acquainted with, and I think pretty easy to understand. So somehow the zeroth one, which is a universal issue, is maybe convergence, and what type would be an issue of eigenfunction expansions. Okay, especially of maybe not very nice functions. Okay, because in many real situations, you can say, well, of course, if it's a very nice function, if it's really smooth, rapid decay, then sure, it's going to work out, and it does for a variety of reasons. In many very interesting applications, it's not so smooth. And of course, you can apply different arguments to try to get from the really nice case to the rougher case, but often these are pretty clumsy and not entirely believable in many cases. So, and already in the case of, let me emphasize, just an ordinary Fourier series, the conflict between L2 convergence and pointwise, just for functions on the circle, is pretty serious. And we can know how to say things by now, but it's a question of which things that we can we say gracefully enough to use them for stuff. An example, because I'm going to make a little bit of a list here first, just to tell you where I'm going. For example, if we ask about pointwise convergence of continuous functions on the circle, well, there's a problem because they don't convert. By bare category, there's a problem. So the answer cannot be somehow trivial. There's overkill if you say, well, just suppose it's very smooth. But that's not such a good answer, actually. And so a more specific, oh, and I should say, then I'll give a few more details before I expand it. The other ones is that when you're looking at spectral expansions for automorphic forms, the eigenfunctions are much more out of control in many ways. You're looking at things on a not compact space. The pointwise values are connected with values of L functions. It's very volatile, so you can't hope for a trivial kind of resolution. And then the first kind of specific thing that we might look at, say, would be, oh, I guess, discretization. Which has to be given a precise meaning of sum of continuous spectrum. And here I'll give some details right now so that you can understand what the issue is. So for those of you who haven't seen this already, on the upper half plane, some Gothic H, then the invariant Laplacian. No, so notice I'm accidentally making it negative definite, so some will have to write a sign. This thing, which many of you have seen, has a L2 spectral expansion. That says F is equal to, at least in an L2 sense, and one has to be careful to understand that what is being asserted. And then there's a sum over all actual discrete spectrum. And let me avoid saying cusp form for a little bit. Non-constant F. So we're summing over what amounts to secretly cusp forms, but it's just discrete non-constant eigenfunctions. And then the constant vertical integral over the line 1/2 of F against ES ES ds. So with the I there, this is a complex contour integral. And that's it, sorry. Where really the characterization of this Eisenstein series might as well be that it fits into this picture, but a sort of an ad hoc description of what it literally is as a function is that ES of Z in the upper half plane is a half sum over CD coprime of y to the s CZ plus D 2S. Okay, I mean, that expression does not explain why it fits into the spectral expansion, not directly. Ah, yes, so thank you. And this is blah, 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 this is the spectral expansion of that quotient where the gamma, the discrete subgroup, is the full modular group. So this is the tiniest and simplest possible case. And so all of the issues essentially come up here already. And again, so now that this is on the board, I can say a couple more things about issues of pointwise convergence. This converges in an L2 sense. And if F is really nice, it actually converges much more strongly. But if F is not really nice, then immediately you can understand that just like Fourier transform on the real line, this has to be construed as an extension by continuity of something that's true on some nicer subspace. So for example, these Eisenstein series, it's maybe not so obvious, but it's elementary, are not in L2. They blow up just logarithmically at infinity. So they're not, I mean, they can't be genuine eigenfunctions because we're integrating a continuum of them. So they can't be L2 eigenfunctions. It's a tiny Hilbert, I mean, it's the separable Hilbert space. Okay, so this integral, the inner integral already is only an extension by continuity. And then the outer integral has the same problem. And it's really very much like, but much more exotic than, Fourier transform needing the simplest hypotheses, which are hard to understand if you're very naive. Oh, suppose f and its Fourier, suppose f is in L1 intersect 2 on the line, and suppose its Fourier transform is in L1 intersect 2. It's like, is that, I mean, what is that? Anyway, but there are more mature ways to talk about it. But those issues arise here much more seriously.
Like a qualifying exam, for instance, in a graduate student, wasn't it? That would have usually been the
Right, that comes up.
Who was you examining?
Let's see, Shimura, Gunning, Pfefferman. Now, yeah, he did, and I knew it then too. Mostly they fought among themselves to see who could answer, but yeah, I had to have my suit dry cleaned after that. It was terrible. Anyway, so nota bene, the pointwise versus L2 behavior. I mean, some of you know this very well, but let's look from that explicit expression of the Eisenstein series, ES of just the point I is zeta function of the Gaussian field divided by the rational zeta function at 2s. And notice it's 2, not s. And on the critical line, this is on the critical line. This is at the edge. So this one is docile. It's just logs. Oh, so if we're somehow claiming that we're just going to look at sup norms of individuals to estimate the sup norm of an expansion, and if you want a sharp result, well, let's, to get started on the basic harmonic analysis here, let's assume Lindelof, sure, or something strong. I mean, that's ridiculous. You can't start out something like that. You might want to prove it later, but you need an alternative. So there's that complication. So looking at that. And then there are further complications if you're trying to look at big groups. For example, then on SL4Z and looking at SL4R, let's say SO4, in addition to the constant, which is badly behaved in the sense that it doesn't decay at all, for those of you who know about this, there are so-called Speer forms, which are residues of cuspidal data Eisenstein series attached to the 2-2 block parabolic. And so these guys are not cusp forms, and they don't decay very fast, and it's hard. I have no idea how to say anything sharp about a sup norm estimate there. And worse, even though there's a qualitative spectral expansion known in general, starting with Langland's at least probably, the details about the non-cuspidal but discrete spectrum, I think, are, well, Muglan-Walsh-Breguet finished it for GLN, I think, but apart from that, they're only scattered results, maybe rational rank 1 or something like that. For SP4, it's known, maybe some other tiny cases, but hardly anything. So we are not going to be able to argue about pointwise estimates based on an explicit knowledge of the spectral expansion. We only have kind of a qualitative knowledge. Okay, so I mean, this is a little bit technical, but it raises some issues. So let me leave that there for the moment. So it's just, we cannot, the point is here, we cannot be too naive. Well, if we are too naive, we won't get anywhere in thinking about pointwise versus L2. The L2 convergence works because one can prove this, well, and a Plancherel should have said, certainly. So there's a Plancherel that works without knowing anything about pointwise values. See, and I only somehow fully realize this, that in many situations, if you have a good Plancherel spectral expansion, it does not refer to the sup norms of the eigenfunctions. Now, if you're a huge optimist, you would say, well, but who cares? Well, if you're a little more critical and realize that you have very dim hopes of being able to start with pointwise estimates, sup norms, well, then you're very happy that Plancherel theorems don't necessarily refer to sup norms. Though, yes, we want to get back to that at some point. But okay. then I think, oh, the discretization, yeah. Now, a thing which still is a little bit technical, but is a further bit of background for a more scandalous thing, is that in talking about the discrete part, the cusp forms, but it's most of the discrete part. In this tiny case, there are various arguments to prove that cusp forms are almost all but the constant of the discrete spectrum. There was a somewhat different argument. I mean, Selberg and Rolke also, and other people early on did some work, but there was a different kind of argument which is much more immediate, to my feeling, if you understand the technicalities. So Fadiev already was doing something like this in '67, and Lax-Phillips then saw this and did something a little bit later. And in the spirit of looking at cusp forms, you consider, instead of the full L2 space, and another reason I tend to like this is its immediacy, and also at least the principle of the argument is pretty clear in general. And in fact, Jacquet adapted this argument pretty generally, though it's hard to read, and it's what is given in Mouglin-Wolfsberger's book in the most general case. There are arguments of Selberg and Langlands and other people, but there's a certain crispness to this that sometimes the others maybe don't have, depending on taste. Okay, so oh, yeah. Okay, Müller, yeah. Oh, yeah, so, yeah, Jacquet saw, after Müller, then Jacquet adapted it to some further. So probably A is going to infinity. A is a real number going to plus infinity. And L2A is stuff in L2 or somewhere, but that's not the critical issue, on the modular curve, so that the constant term, but well, let's write it, equals 0 for y above A. So the constant term, this is the constant term, is eventually vanishing. So sometimes you would call this a pseudo-cusp, well, if there's some eigenfunction condition, but this is part of a pseudo-cusp form condition. Yeah, the constant term eventually vanishes. So what people proved, and I think really Fadiev had the idea, and then Lax-Phillips emphasized it a little more, but so this was known certainly since then, and I think it's page 206 of Lax-Phillips. You can just go directly there because the rest of the book is kind of disconnected from it. But is that so that now here's the time where we say, well, take that Laplacian on this truncated thing. See, now all of these, here's where the cusp form condition says, well, this is a huge amount. All of these guys are in that truncated space because their constant terms vanish entirely. This is discrete, meaning there's no integral anymore. There's no continuous spectrum. Okay. Now, if you hadn't thought about these things some, you think, so? Well, and it's, okay, so let's have that there. And then you think, well, fine. Then also, Colin de Verdiere showed around 1980 that really part of the background for this argument, so there was a compactness of an inclusion, so a Relic-Kondrachev type lemma in that context showed a meromorphic continuation of Eisenstein series by expressing the Eisenstein series in terms of this resolvent. And now, see, by 1980, everybody knew that the conclusion of the theorem was correct, that the Eisenstein series had an analytic meromorphic continuation because there are 5 different proofs at least, especially for SL2. So the fact that the proof might have been incorrect, you couldn't tell it from the conclusion because the conclusion was true, right? It's one of these awkward situations. But, well, fine. So it's a little provocative. Even if it's wrong, who cares? I mean, we already knew that there was a meromorphic continuation. So it's not so scandalous. So, but let me say the first tiny scandal, it's not really a scandal, but confusion is what are the new actual discrete spectrum, so actual eigenfunctions of some version of delta on L2 on this restricted space. You know, in other words, where did the continuous spectrum go? Like, really, what happened?
You should emphasize that cusp forms in there.
Right. Yeah, so whatever the decomposition is, it's still that sum over cusp forms, and plus constants, fine, and plus what? And you think, well, you threw away the Eisenstein series. Well, no, you didn't. Because truncated Eisenstein series are in there too. So something like this. So that means just kill off the constant term above height A. So this is, in this case, the truncation of an Eisenstein series is easy to understand. You just kill the constant term. Now, in general, the thing that you make by doing that won't be continuous. And somehow it looked at sideways. Typically, it's going to be the new constant term then will look like this. Somehow, at best, so there's a definite jump. So it's not continuous. At best, it might be continuous at best. But so there's a continuum of these guys. Do they become eigen? I mean, they can't all be eigenfunctions once again because there's a continuum of them. Not to mention the fact that if you had never learned any analysis and don't really understand about unbounded operators on Hilbert spaces, or if you think that a purely measure theoretic viewpoint is enough, and I remember when Selberg and Cohen were arguing in that room in 1980, Peter was there and I was there. Who else was there? Maybe nobody else. Maybe. There was this big discussion about, well, but it's an eigenfunction almost everywhere. Okay, some people laugh, but that's pretty worthless, except wait.
By the way, is A bigger than 1 here?
Probably. Did I say it's? Yeah, well, it's part way to infinity, so it's obviously bigger than 1. Yeah. Yeah, A should be bigger than or equal to 1 for a lot of reasons. Well, okay, so if you're thinking that it's the real differential operator, and if you recognize the fact that a differential operator applied to these things, just looking at that one piece of it will produce a distribution, then there's got to be a hitch. So just thinking about this means that whatever this delta is, the true thing on L2 gamma A is not exactly just plain delta. It's not the distributional derivative, or else it is, but you have to interpret it in a different way. And oh. So
I have a simple question.
Yes.
Now, does the Laplacian leave that invariant, or are you projecting on there, or what are you doing?
oh, it does, well, I keep putting it in quotes for the moment, okay? It does leave it invariant, yes. No matter how you reasonably interpret it. Well, I'll say a different thing.
You define the core domain and then you make the self-adjoint.
That's right. So that's, yes. So I'm trying to approach this, but that's really the issue, is that, see, I didn't believe when I was younger that all of this technicality stuff about the domain. Yeah, self-adjoint. Okay. But it's not trivial to see that it would make a difference if you, because even if you're solving differential equations on the line in an elementary way, like a Sturm-Liouville problem, you say it's harmonic in the interior and has some boundary, like vanishes on the boundary or something. You think, great, so it's an eigenfunction for a Laplacian. But if you say, well, the function is really that, and then it's 0, you have corners again. So if you differentiate correctly, it's not an eigenfunction, but the actual self-adjoint extension is ignoring those deltas at the end. Aha, but like, is that legal? Because it's certainly wrong to say that, oh, it's an eigenfunction almost everywhere, because then there would be no condition about boundary values, and you'd have a continuum of things, and it would certainly be wrong. So this kind of confusion, which certainly existed in my mind and many other people's 30 years ago and so on, is brought to the forefront by trying to understand a thing which is pretty old. So in this case, this is sort of an introduction to what a Friedreichs extension. So Friedreichs self-adjoint extensions of semi-bounded symmetric operators. So now also, I was confused years ago in reading Risha Naj that symmetric actually means Hermitian symmetric. It's not the difference between bilinear and so it means Hermitian symmetric, but it doesn't mean that the domain of the thing and its adjoint are the same. So a symmetric operator has that property, but it's, and of course, only for V and W in the domain.
You done your degree at Stanford?
And taken Fourier integral operators over and over again.
Ralph Phillips, this would never be an issue.
Well,
This was every course was
well,
self-adjoint.
you know, I went to Princeton instead. What can I say? It's like, well, the weather is better in Stanford. But okay, so this is the condition. But still, in general, if you figure out how to, so symmetric really means, oh, and in general, I'm going to try to insist that all of these unbounded operators are densely defined. So the domain is dense, which is not something I'll try to fool you with. But so the condition that T is symmetric really is that its domain is contained in the domain of its adjoint, but in general, they're not equal. And in simple situations, like the Sturm-Liouville problem on an interval, there's a continuum of not mutually comparable self-adjoint extensions. So it's not that there's a canonical one. If there is a single one, that would be the case, I guess. It must be that if you take the graph closure, it's self-adjoint. Oh, but this is called essentially self-adjoint. And then the problem is, back when everything was in typewriter font, when Harishchandra says, blah, blah, blah is known to be essentially self-adjoint, I misinterpreted that as meaning, it's like, it's more or less self-adjoint, which didn't help anything because there were no italics then, right? It was typewriter font. Anyway, so in general, there are a lot of different extensions. So especially if you've imposed some boundary conditions. So there I said boundary condition, finally. But still, if you specify everything, then the Friedreichs extension refers to a specified domain, and inside the domain is encoded stuff about boundary conditions in even an abstracted sense, if you like. Okay, so let me describe that just a little. Oh, and I should say, give a date. So this was from 1934, so just a couple years after Stone and von Neumann did the somehow maximal self-adjoint extension, but I think they only cared more about existence for purposes of legitimizing quantum mechanics, so that their maximal extension was not as clearly defined in terms of some physical context, I think. Now, and also you have to watch out, because any two self-adjoint operators that are comparable in the sense that their domains are comparable are equal. So minimal and maximal must not be taken literally because it's false. But it's rather it's some other process that is more complicated, so the names are misleading. So here, So here, let's call delta A be the restriction of delta 2 to smooth things on that quotient whose constant term vanishes above A. And then this thing, I think I'll actually try to tell what it is, how it is defined. So first of all, let's call this for a second S, or maybe minus this S. So this is our semi-bounded operator, and you define a new inner product where these are in the domain of the uncompleted thing to be sort of unsurprisingly, maybe you add 1 to it, it hardly matters, to be the plane thing in L2, okay? And then you can let, then a certain kind of H1 Levi-Sobolev space is the completion of the domain of that restriction in the +1 Sobolev or Levi-Sobolev norm. And now, see, again, it's important to understand, domain includes boundary conditions. Some of those boundary conditions may be lost, though, when you take just a H1 completion. So if you have very high codimension things, those will be forgotten in the limit. So there's certain things you can't do. But see, in physical situations, if you have some nice domain, then the boundary is of codimension 1, and it's not hard to show then that that is, as it will be respected by Sobolev 1 topology. Okay, so then, and there are a lot of things you can say about this. I mean, it's very explicitly described that, let's see, the completed thing on V is described by, so characterized completely by saying this in a limiting sense. So on the completion, it makes sense, blah, 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 blah. Oh, this is a comma. Oh, okay. So you can manipulate it in ways that a kind of axiom of choice construction couldn't be manipulated, certainly. Oh, so then the upshot, if you examine this in a little more detail, which is not hard, and I put some essays online discussing this. I won't do the details right now, but the point is, and Colin de Verdiere wrote this down, but it was a little bit terse, and I couldn't figure out his context for a long time, is that this equals W for suitable functions V and W in the vector space if and only if they're in the space, okay? So we're only talking about things that vanish above, if and only if this is W plus some constant times the distribution that is evaluate constant term at height A. I should have named it. Well, so that's the boundary condition. See, all of the vanishing above that can be expressed in a way that is just orthogonality to some L2, but just at the edge, that condition cannot be made in the L2 topology. It is made only in the H1 topology. And going with this is that the eigenfunctions for this, okay, and now these really are legitimate. They're absolutely kosher by the most extreme standards. So, and say non-positive or non-negative, however you like, so that their eigenvalues are not just, it's not just a heuristic that their eigenvalues are, they're real and positive or negative, whatever. Well, what are those eigenfunctions? Okay, so cusp forms, yes, yes, yes. Nothing changed for them. When you see this, it's not that you've mutilated the thing on cusp forms because their constant terms are all 0 anyway. And V in the domain, I should really give this a name. Let's call it eta sub A. So that's evaluate constant term at A. V such that Laplacian this is equal to lambda V plus some constant times A to A, and A to AV is 0 because this thing has to be in the H1. If it starts out with its constant, if it's smooth, starts out with its constant term vanishing at height A, and you take a H1 limit, it's still got to have constant term 0 because taking that H1 limit remembers the integral across that line segment, okay? So there are two conditions. So it's the obvious thing which was relaxed because the catchphrase that I like is that these Friedreichs extensions of restrictions can ignore certain distributions. Okay. But it's not just that. It's not that everything that fits into this is an eigenfunction, and it's not the case that all of those numbers are necessarily real. That would be a gaffe, and I'll illustrate this in one moment. You also have to require, because a genuine eigenfunction, if you look at the construction of the Friedreichs extension, all of the genuine eigenfunctions are in here. So I should emphasize that all of the genuine eigenfunctions are in there. So if you construct a thing that you think, because you forgot some aspect of the Friedreichs construction, so if you just jump on the fact that you can forget a distribution, but you forget that there's another condition, you will include too many numbers lambda. And you think, well, it sounds kind of technical. Who would do a thing like that? Really, I mean, only a silly person would find themselves in such a technical situation, surely. But now, of course, I probably wouldn't be talking about this if it had only been discretizing the spectrum and meromorphically continuing Eisenstein series, because everybody knows you can meromorphically continue Eisenstein series. And just figuring out this is not a big deal. But there's another story that made it impossible for me to permanently ignore this business. So Haas in 1977 did some numerical work. Did he use collocation? Yeah. Okay. Did some numerical work, the collocation method, which I don't claim to understand, to try to numerically determine eigenfunctions of that same Laplacian on this modular curve. And when you set it up numerically, then instead of having an abstract quotient, you have to put a grid and da-da-da-da. And now, probably most people here know, maybe everybody has seen this picture. I tell my students they have to practice drawing this so that they're credible. Because if you can't draw this accurately, it looks like you're a parvenu. But anyway, so they're corners. And actually, this gets wrapped around, too, so that the actual modular curve has some kind of a pucker, maybe at a couple spots. I mean, it's not a big deal, but it's a subtlety already here, because the Riemannian structure is getting a little messed up. And if you're doing it numerically, then there is a definite, acute angle. Or, in fact, if you're looking at even things, then you include a flip back and forth, and you get another corner. And Enrico told me a subtlety that I hadn't really appreciated is that somehow this corner turns out not to be as troublesome as that corner. It's like, who knew? I don't see it. So what he appeared to do is he had computed a list of alleged eigenvalues where some of the time you'll see a flip of sign here, but it doesn't matter so much. So these guys have got to be non-positive for genuine eigenvalues. Okay, and he computed, supposedly, though not as scrupulously as already Dennis Hejhal had been doing, and maybe you had been some people had been, and Cartier certainly had been computing, I think, before Haas even. People had been, and it was not such an easy time, computed apparently some things, and Hejhal and Stark eventually, Audrey Terrace got a hold of that list. It was a thesis. Where was it? Somebody knows. It was in Germany somewhere. People got a hold of the list, and Well, Stark and Hejhal are the kind of people who look at a list of decimals and can pick out known zeros of L functions. Okay, so some zeros, so the spectral parameter values S were apparently a bunch of other stuff and zeros of the rational zeta and of LS of the quadratic character, this. So for -3. So, I mean, yes, you can anticipate there's some connection here. But so then Hejhal checked. It was a year or two later maybe, but so certainly.
One of the most interesting things that you're not saying is how everybody then gave explain philosophically why this has to be true.
Well, right. Well, yeah, I mean, if you just.
Everybody was explaining why it's true.
Okay, because, yeah, I should say, but probably almost everybody in the room knows that, people for a long time have been saying, well, you prove you-know-what by finding a self-adjoint operator, blah, blah, blah. So then here, well, if we have discovered in the dawn of the age of computers at least some data that makes that plausible, then it might be possible to do that. Not that there was any causal mechanism proclaimed or even imagined, but if the fact is there, then it is at least plausible that you could prove it. Whereas if the fact is not there, then you shouldn't probably try to prove it. So it was provocative and true. People were rationalizing, and that was when I was just starting out. And right, it's appealing, and it was a great thing. Though when you try to look at this stuff, it was very hard for me because I had not studied much analysis of the relevant sort. Modern, post-1930 is modern analysis, is that right? But yeah, there was a lot of philosophizing. So at latest by 1979, because I think there was some time lag, Hejhal recomputed and much more carefully. And he got, there were some numerical inaccuracies, and they got almost the same, except the only thing that were dropped, it was exactly the fun zeros that were dropped. And like, you think, wait a minute, how many garbage computations produce garbage that is zeros of L? Yeah, well, it's a very high quality garbage. You think, wait a minute. So, okay, even if his computation was wrong, it was wrong in a very interesting way. Okay. And in fact, Hejhal was able to examine, I didn't really understand the collocation method, but he was able to examine the situation well enough to see that what Haas had actually solved, numerically, was, so this is an automorphic delta at this root of unity, something like that. Okay, so instead of 0.
In other words, the way you state, so the easiest way to understand it is he was solving the equation by discretizing, and he was allowing a logarithmic singularity at the point omega without realizing that
Yeah,
the logarithm is so slow, he never realized that it has singularity.
Square degree that relates to that coordinate. Pick up the coordinate with the square degree.
Yeah, so in case you didn't hear, the point is you can't pick up this 60-degree angle with a square grid, apparently. Whereas the square coordinate, okay. Now you think, well, so it's just silly. He wasn't solving the homogeneous equation. But if you'd just been reading about Colin de Verdiere's proof of blah, 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 but there are ways to make a thing ignore distributions. So then, but let's consider.
Now, you should give Hejhal more credit. He then realized that the Green's function.
Oh, yes, sorry. Yeah, so people did look at, they did that, well, yes, so this then says U is a result.
Logarithmic singularity at the point omega, then indeed you do get the zeros, and Haas was correct.
Right.
But this doesn't put the zeros on the line, because once you allow logarithmic singularity, you no longer self-adjoint.
Right. So there is an operator that's perfectly legal, but as it stood, it was not self-adjoint, so that you can't reach the desired conclusion. Okay. But so you want to make it self-adjoint, yeah. Which just a few minutes ago, though, we learned might be possible because you can do this crazy thing with Friedreichs extensions of restrictions. So then, let's consider something like, f in L2, so that f at omega is 0, and call this something. Call this v sub 0, say. So it's, well, we have to be a little careful because pointwise values don't make sense here. So fine, you have to say, might as well retreat to test functions. Okay, so, and then we let this, and so the evaluation, let's say f goes to f omega, let's call theta or something, just to use a different letter. So this space, test functions that vanish at omega, let's call delta sub theta. Okay, so here we have a domain. On that domain, and this makes sense, it's a continuous functional there. We've restricted the actual delta on smooth functions just a little. And so you think, well, there's several things you can think about. So then, the Friedreichs extension, well, is self-adjoint. Adjoint. Fine. So then, so this is kind of chess notation. So
Chess, that's a plan.
There's been no inflation. Well, okay. So how? Okay, maybe it should be this then. Anyway, so does that imply, actually, then that the eigen? Okay, maybe that's about right. Okay, so the eigenvalues are real. Okay, and this is actually true because that's correct. Okay, so the technicalities are correct. And did we recover? So this is the questionable part. Did we recover those things computed by Haas, the numbers from Haas, by this subterfuge? Have we made it legitimate? Well, it's like when you think, wow, yes. Then you don't want to dispel your feeling of happiness right away, so you just don't think about it for a while, probably. But then, well, it turns out then, you go like back and forth when you're trying to understand this, especially if you approach it not having taken the Fourier integrals course over and over at Stanford, and you're just learning this. Well, we forgot the condition that we must require that theta of such a solution is 0. Otherwise, U is not somehow a legal eigenfunction. Now, it's just not an eigenfunction for that actual extension. And now you can say, well, why not? It looks like one, But the technicalities of that boundary condition. See, this is what I'm calling a boundary condition. It's just a little abstracted. It's not on a physical boundary, but it's the same kind of thing. It's in some negatively indexed Sobolev space, and I haven't said much about that. So maybe just at the very end, I'll try to put order to some of this discussion. We forgot this. Well, still, you could go back and ask, well, which of those actually satisfy this? But then it becomes very difficult to answer that question. It's certainly not obvious that they all do. It's not obvious that any do. It's not elementary. And
I should mention that in Colin de Verdiere, of course, there is a first ideal, hopefully,
That's right.
value, which is 8 point something. But then, just by comparison, you can get lower bounds for the eigenvalue by
Oh, okay. And,
So
oh, sorry.
They got the lower bound. If the lower bound is greater than 8 point something, okay, then you're, that does not work. He got the lower bound 6 points. So at least that potential possibility was not excluded.
Right.
And he said that to do a numerical computation was really not feasible. because
Yeah.
of very, very slow convergence of probabilities from the numerical convergence.
Yeah,
So
so,
this we find in Colin de Verdiere.
right, so there was numerical evidence against. But now, in fact, even this, I tried to plan a little drama, even this is wrong. No, many of the assertions are correct, but there's an underlying problem. If you hadn't studied carefully enough, you would have overlooked the fact, so oops, this theta is not in the suitable -1 Sobolev space, whatever this is. It's things with, it's in h minus 1 minus epsilon for all positive epsilon, but so what actually happens, I mean, you can delude yourself into anything. I mean, these things are not very tangible, especially if you're not doing numerical computation. So what happens is that actually taking the limit, so the completion, the completions that are involved in making that Friedreichs extension, just forget about the condition entirely. And so now this thing is just the original Friedreichs extension of the essentially, the italic, essentially self-adjoint delta, and theta is gone from the picture, so it doesn't even make sense, okay? Oh, okay, but now after you learn that, and I think that was, oh, and see, this analysis of the difficulty might be attributed to more recent times, because the discussion then was not quite in these terms. So part of the reason that I was cheered up, and I think encourages us, is that we have when you get all of this straight, then you have a much quicker numerology to exclude certain things that couldn't exactly work as they stand. So if you can do experiments that return a sort of negative result but are educational much faster, it's a great thing. Okay, well, then the next step is, how do you fix this? How do you repair this? Well, among other things, you could look at a subspace. And Colin de Verdiere already suggested this. So you could look at just the complement, the orthogonal complement to cusp forms. For example, Colin de Verdiere already suggested this. I think with only vague discussion about a Sobolev problem, this numerological condition. I mean, I think he might have been able to say this, but he somehow didn't. The virtue here, and then you ask, well, but now we're abstracting things. So you look then instead at somehow the projection. And now, here's the point where you really have to be working in Hilbert spaces and not Banach spaces, because so instead of the more natural, the more naively natural hierarchy of, differentiable functions, well, both locally and globally, the Sobolev spaces that are L2 Sobolev spaces have a lot of features that are better, and since they interleave, then, well, and they're Hilbert spaces, you can talk about projections if you can tolerate just a little offset due to the Sobolev embedding theorem. So you could project this, automorphic delta at omega to sort of a non-cuspidal part. And then if you look at the spectral decomposition, and I think Colin de Verdiere already wrote some things about this. Well, this is, it turns out to be in already by Hardy and Littlewood from 1918 or 17. It's, how shall I say this? So it's in L2 non-cuspidal.
They use that terminology.
Pardon?
Some theorem of this is used to get.
Oh yeah. So it's at their moment.
Estimate of zeta.
Yeah, their estimate on zeta. This is in that Hilbert spaces with associated operator delta restricted to that. And delta does stabilize the orthogonal complement of cusp forms. H maybe -3/4 minus epsilon for every epsilon. Oh, which is inside H minus 1. So then that would make that legal. Okay, and I'll just wind down without writing anything anymore. Well, but now you've done a weird thing to this Dirac delta, the automorphic Dirac delta, because see, if you were only able to say that it was an H minus 1, well, it's definitely not localized at a point in a physical sense, because it's the full L, at least not to my understanding. So L2 of a physical object, then you can do local Sobolev theory in a way and reduce to the circle, and you know what the bounds on things are. But then when you project it to some ineffable subspace of the Hilbert space, a thing which had a physical meaning there has what meaning? See, it's strictly inside H minus 1. So because you're on a two-dimensional thing, it's even locally not in H minus 1, so it can't. We know a classification of distributions on a smooth manifold supported at a point, so it can't be that. It's compactly supported, I think, but it's like, what is it? It doesn't have a clear physical sense, so it becomes a little harder just to do numerical experiments then. So I ran out of time. But thank you for your attention.